It's great to see such a popular day, isn't it, Joe? It's wonderful. Get everybody in that we can so that they can make the most of this talk. So I'm delighted to welcome Professor Anastasia Fialkov from the University of Cambridge, who's going to talk to us about Olbers Paradox, why the night sky is so dark. Over to you.
Thank you very much. Thank you very much for the invitation. It's a pleasure to be here and to give this talk. So I was asked to talk about why the skies are dark at night, and I went on all the way to modern cosmology, so bear with me. So the easiest answer that every kid will tell you, and that Google AI actually gave me when I typed that into my search, is that obviously sun goes down, skies get dark. We all know that, it's very natural. But what's the real reason for that? Is that the only reason? So skies are dark, we know that since we were born, and these dark skies inspire curiosity and drive people's imagination. So there are many myths and legends why sky is dark. People associated it with gods. So when we look at the dark sky, we see just a few bright stars. Naked human eye can see around 3,000 stars, and that's it. So for us, just as we look out at dark sky, we see that it's mostly dark with a few bright objects. But of course, if we use powerful telescopes like we have today, we are very fortunate to live in the 21st century when we have these wonderful telescopes. We see many more objects that are not resolvable and to which our eyes are not sensitive. And as we progress, so here on the left is the picture taken by Hubble Space Telescope, which took wonderful, beautiful pictures, but it actually was superseded by James W. Webb that sees many more bright objects and deeper into the cosmic past. There are a few reasons for that. JWST is more sensitive, and also it looks at slightly different wavelengths. So those let it see many more objects. But still, even with these powerful telescopes, we see that there are many dark spaces, and the sky is basically a collection of bright spots on the dark background. That's for Jerry. So, but actually, if we look into crowded regions, the universe is not uniform, right? We know that our Milky Way has many more stars than the average. And if we peer into the center of it, we actually see bright skies. So there are regions where sky is bright at night. These are very crowded, full with stars. More modern telescopes discover many more galaxies. So for example, this dark energy survey is measuring 300 million of galaxies. So the skies are not empty for sure. But still, even with that, most volume or most of the observable universe seems dark. And why is that? So is it really a simple sun goes down and it's night and it's dark, or is a deep meaning behind that? And they'll show you that actually there is a deep physical meaning why do we see sky as dark, and it's not always the case actually. So this question goes back centuries back to Copernicus, who postulated that sun is in the center of the universe. And the Earth rotates around it, and then there are planets, and then there is a sphere of stars, the celestial orb, onto which all stars that we see are glued, basically. So that was early 16th century, and this actually idea started people thinking and originated. So that's where modern cosmology originates. So it took centuries from Copernicus to realize by scientists in the 20th and 21st century why actually the skies are dark. So In the second half of 16th century, there were several people thinking about this problem, including English Thomas Digges and Giordano Bruno, William Gilbert, who actually thought that stars are not glued to a sphere, but the universe is infinite. So already in 16th century, people started thinking about the infinite universe, and Giordano Bruno even thought that there is no center to it. He even thought about life around other stars. It was so progressive. But the first person who postulated the dark sky paradox was Thomas Digges. He was the first one to translate Copernicus' work to English, and actually that was a kind of start of popularization of the theory already then. So in their view, still sun is in the center, and the stars are not glued, they're distributed infinitely through space, and there are random distribution basically. Everywhere you see, you should see a star. So these ideas became more solid by mid-17th century with René Descartes, who also thought about this and got formulated in terms of Olbers Paradox in 1826 by Heinrich Olbers, who kind of wrote it down, saying that the darkness of the night sky conflicts with the assumption of the infinite and the static universe. So he didn't know the universe expands, as we are fortunate to know today. So for them, the universe was static. And they thought all stars were like our sun. So they thought that if there are infinite number of stars randomly distributed through infinite static universe, the skies should not actually be dark. And the fact that we see skies as dark is a conflict, a paradox. So as I already hinted, it took centuries literally, and it's only the progressive work done in 20th century with both theory and observations by Einstein, so general relativity observations by Hubble, and others that led us to answer this question. And so I'll show you today why the skies are dark, actually. And so already here, this is a cartoon of what we know today about the universe. You see that it's way more complicated than just this picture, right? We made a lot of progress. Yay. And there are several steps that I'll walk you through here that all conspire to the fact that we see the sky dark. So simply put, Olbers Paradox tells us that there are infinite number of stars, and basically every line of sight, so any direction we look, should end on a star, either close to us or far away. And actually, that's why he thought the sky should be bright. So it's like being in a forest and either shooting an arrow or just looking around. Everywhere we look, we see a tree. So we don't see horizon behind it. So that's the analogy they use to demonstrate that also the sky should be bright and not dark. Right, so I did copy-paste all the stars to demonstrate that we expect to see the bright sky at night. So mathematically, we can prove that mathematically if we take sun-like stars and randomly distribute them throughout the universe, infinite universe and static, we get that actually the observable surface brightness, it is called how bright the sky is in every direction, should be independent of the distance of the object to us. So let's look at let's just divide the space into small spheres around us at different radii. And we know if we take an object and place it far away, so if we take our sun, place it further away, it will seem dimmer because we are looking at a distant object, and its flux drops as 1 over r squared. But if we have a uniform distribution of such objects, the number density or the number of these objects should actually grow as the area of the sphere or volume of the sphere, which for thin spheres grows as r squared. So if we sum up the contribution that each sphere gives us to total observed light or surface brightness, we get r squared times 1 over r squared, which r squares cancel, and we have a constant. So it doesn't matter where we look. All spheres contribute the same total light. So sun here would be at the same surface brightness as a sphere of distant suns far away. And this is because there are very few bright objects close to us, but there is infinite number of distant objects far away that overall sum up to total brightness. So mathematically, in this situation, in this setup, we do get that sky at night should be as bright as sky during the daylight when we have sun dominating the picture. Right? So that's how Olbers was thinking at that time. So this is a little video from Wikipedia. So that shows that indeed if we have sun but distributed at random distances, eventually we will get it filling up the whole volume. And the surface brightness of the whole sky should be the same as the suns during the day. So over centuries, there were many solutions proposed. Even philosophers were thinking about it, of course, and poets, for example, Edgar Allan Poe wrote a literary work called Eureka in 1848, where he considered cosmogony, and he also thought that the universe was actually non-static and infinite. It was not based on any mathematical or physical concepts. It was just his intuition about how the universe would be and his view, right? But that's amazing. So when he published that, there was a kind of a press release, and he thought many people will come, hundreds, but in fact only 60 turned up. And it was not very popular at that time, but it's very interesting to read now that we know the answer. So other solutions included, for example, if there is gas and dust intervening, they would absorb the light from distant objects, make them even dimmer. But actually, that doesn't solve the issue, because then this gas and dust would irradiate the photons back, because they just cannot absorb infinitely. They start emitting light. And so eventually the universe would be hot and bright anyway. The universe is finite also doesn't work, because we now see with our telescopes that it actually is infinite as far as we can see. The universe had a beginning. We know the Big Bang theory, and it does tell us that the universe had a beginning, so that's part of an answer, but not all of that. Another hypothesis is that might be early stars were less bright, but actually we think today that they were actually brighter. If you take a star formed very early on in cosmic history, it didn't have chemical elements such as star has today. It was, as a result of several astrophysical processes, much bigger than the sun. Some theorists say that first stars might be 1,000 times bigger than the sun, and they were in fact brighter. They lived shorter, but they were brighter. And then different combination of factors that we have today in modern cosmology that actually solves the issue, which includes several things I'll discuss in a moment. So we have the beautiful Big Bang theory that actually is backed up by observations today. It's not just theory, we're proving it. That tells us that the universe started as a very compact and hot entity that had a phase of exponentially fast expansion in first instances. So it's this bright point on the left-hand side here. There is a period of very fast expansion when there was no matter yet. There was pure energy, and then this energy condensed into particles as we know them today, slowly through several processes. As the universe expanded, which we also know from observations, it actually cools down, And these particles at some point form first atoms ever, which are mostly hydrogen. And as the universe keeps cooling down, these particles get together due to gravity, eventually form stars at some point that illuminate the universe. So this is the Big Bang theory. And we also have our general relativity, which is amazing. So Einstein conceived it as just pure thought experiment. But then every experiment we do today, every observation that we do today, either on the scale of the whole universe or looking very closely on small scales, close to black holes, this theory seems to hold. So it's an amazing, beautiful work of art, in my view. And one of the outcomes of this, or postulates of this theory is that speed of light is finite and is constant in vacuum everywhere. So that's another ingredient that we have that contributes to the fact that the sky is dark, actually. And another piece is that the universe expands. So I'll talk about it a bit in a few seconds. Okay. So the fact that the universe had a beginning is actually helping us very well, because if we have that stars form at some point, only those that are closer to us than the speed of light times the age of the universe will be within our observable horizon in this case. All stars that are further away, they just simply didn't have time for their light to reach us, because there was no enough years in the lifetime of the universe. So in fact, we see less stars, not an infinite amount, but only those within this effective horizon. So the fact that the universe expands helps us also, because it's like the Doppler shift of the sound. When the ambulance passes, you see that the sound gets lower and lower in frequency as it goes away. Same happens to light in expanding universe. So sources that are further away from us seem redder than closer to us, so at lower lower frequencies, larger wavelengths. And also, because the universe expands, their flux actually drops faster than 1 over r squared, so the cancellation in the Olbers calculation doesn't work so well. So the distant sources seem dimmer in an expanding universe than in static universe. In addition, if we have a source in the wavelengths that our eyes can see close to us, if it's far away and receding from us, it will actually move into the wavelength region where our eyes are not sensitive to it anymore. So there is a band of wavelengths that our eyes can see, and most of the early time sources or distant sources redshift outside of that band, so we don't see them anymore even though they are there. So we need telescopes like JWST, which actually sees light in infrared, so redder than our eyes can see, to access these very early sources. And one of the facts that JWST can see further than Hubble is that its filters are redder, so it sees sources that are further away from us. So Hubble Space Telescope can detect galaxies all the way out, those that are at 400 million years after the Big Bang, so roughly here, if this is a history of the universe, and we are here on the right. Hubble telescope can see all the way out there, so 400 million years after the Big Bang, and JWST can see even further, around 200 million years after the Big Bang. So this is an example of the first galaxy, or early type galaxy that JWST sees. It doesn't look anything similar to our Milky Way with beautiful spiral arms. It's just a blurb. But that's a real galaxy very early on in cosmic history. And with JWST, we can actually see those. And still, the sky is not dark. Another reason is that actually sources are not distributed uniformly. Now we see all this, what we call cosmic web. It looks like a spider web, and we call it cosmic web. This is a structure of the universe on very large scales of hundreds, megaparsecs, even gigaparsecs. So we see that there are empty regions. So these gray regions are almost devoid of matter. They are called voids, while there are more dense regions where are many galaxies. So bright regions here are populated by galaxies, and they are very high in density, in matter density. And this is, again, because of gravity. Matter pulls itself together, and the universe started soon after the Big Bang. It was not completely uniform. There were tiny oscillations in matter density that grew to form these clusters of galaxies and other regions that are much more empty and void of galaxies. So of course, if we look towards a crowded area like our Milky Way, we will see a lot of light coming out. But other regions, like this big void, doesn't have galaxies at all, so it will look dark. So this is the map of early fluctuations in matter that we see with our telescopes today. And actually, this is an example of sky that is bright in microwave. In microwave, unlike in visible light, the sky is not dark. Actually, it's glowing. And that's the image of it. That's what actually real telescopes see. So every point is just like a map of the sky. So every point here can be associated with a line of sight. And what we see is that on the timeline, it's here soon after the Big Bang. The universe at that time, just very shortly after Big Bang, didn't have stars or galaxies at all. It had tiny fluctuations or oscillations in matter content, with red spots here showing density slightly higher than in blue spots, just a fraction of 1 to the 10 to the 5, basically. There are tiny oscillations in the overall matter density field that eventually grow into galaxies and stars that we see today. So in some regimes, there is no dark sky at all. And actually, I want to relate to something I'm doing to my research, which is observing the universe in radio. And it turns out that the universe, even the black spots here, are not empty, right? It's mostly vacuum, but it also is populated with gas, which is mostly hydrogen. This is the easiest element to form, and that's hydrogen formed in abundance at very early times. This is the first element in the periodic table of chemical elements, and it existed throughout the cosmic history, so already here, soon after the Big Bang, the universe was filled with hydrogen atoms. No stars, no galaxies, just hydrogen gas. And actually, this hydrogen produces radio photons that we can observe today. And this also will be measured through the whole universe, through the whole sky. And the sky is bright, actually, in radio. So this transition that we want to observe is actually a forbidden transition. It doesn't happen naturally in the lab. It takes 10 to the 15 seconds for one atom to produce such a radio photon. But the volume of the universe here is so huge that we can actually collect enough of these photons to observe today with modern radio telescopes. This radiation, of course, redshifts because of the expansion of the universe. So we are looking today at frequencies around the radio FM band, sadly, which contaminates the cosmic signals. But there are techniques to observe it still. And this signal would be sensitive to everything that goes on here, even beyond the reach of James W. Webb Telescope. So we expect to see the whole history of the universe in this line and detect signatures of the first stars through indirect impact on the signal. Telescopes throughout the world, there are many radio telescopes that look pretty simple. They don't look anything sophisticated like JWST, no golden mirrors here, just a bunch of radio wires. But they actually have power to reach all the way to the first 100 million years after the Big Bang and observe these radio signals. And this is actually the first data from the station. The square kilometer array is now being built in Australia to reach far into the past universe and observe this radio background. So the glow of the hydrogen atoms. And this is the first ever station that was built. It's just it's this year's news. And the first data that they collected, so we see the bright stripe is our galaxy here, and the lesser bright, so it does look dark, but it's not, it's just relative scale. This is an emission from the rest of the sky. A bit of science more. So what do we expect to see with the signal? So here we see fluctuations similar to what we saw in the CMB, like those. But they grew and evolved, and now they contain information about first stars, galaxies, and we can actually count and assess how many stars and galaxies were there through the whole history of the universe. We can say how hot or cold the gas was, how the stars affected the background universe, and so on, a lot of information there. I think it's very fun to live in 21st century now that we know the answer to Olbers Paradox, why the sky is dark. It's not completely dark. It depends on where you look. But still, there are many mysteries to solve. We don't know what, basically, what we see is only roughly 5% of what there is. So this chart shows total amount of energy in the universe. And it shows us that around 70% is in a form of dark energy, which contributes to accelerated expansion of the universe today. And that's what Einstein referred to as his biggest blunder, the cosmological constant that he omitted and tried to forget about it, but then observers actually measured it. So it turns out that 70% of the total energy in the universe is in a form that we cannot explain at all, other than postulate it's a constant or try to measure how constant it is. 27% is in a form of matter, but the matter that we don't know the nature of. We cannot touch it, we cannot see it directly. It's called dark matter. We see its effect on stars and galaxies, the bright matter, but we don't know directly what it is and what is the physical particle physics nature of that. And only about 5% is the matter we made of, this disk made of, all the stars are made of. So just 5% of total energy in the universe gives us light that we can see and use to map the skies. So I don't know if we will answer this within this century, or it will take many more centuries to answer these questions. I hope not, because I'm really curious what dark matter and dark energy are. I think it's embarrassing as a physicist that we only know this tiny fraction, but that's the reality of it. And I'll stop here, and thank you very much for attention.
Thank you so much, Anastasia. What a fantastic, fascinating talk. And I have to say, I really appreciated some of those literary references. Understanding Olbers Paradox through the eyes of Le Petit Prince. I mean, that's not what I was expecting this morning. Thank you. We have some time for questions. We have one over there, one at the back. Let's get started with a gentleman there, and then right up at the back near the AV.
You mentioned that only 60 people turned up for Edgar Allan Poe's idea, but what reaction did he get? Did it make it into the scientific literature?
Sorry, what
You mentioned that only 60 people turned up to see Edgar Allan Poe,
Yeah.
but what reaction was there to his idea,
Yes.
and did his idea make it into the scientific literature?
So it was not, well, I'm not an expert on that, I just read briefly about it, but his ideas were not well received by other poets, and they thought he was just talking nonsense, basically. And it took really many decades until his ideas appeared to be consistent with reality magically.
And up at the back near the AV.
So at the present time, is the sky getting darker or brighter?
It's a good question. So there is accelerated expansion, so further distant objects are moving away faster and faster from us. They're redshifting faster and faster, and so we see less and less. Basically, our observable horizon shrinks at the moment. And there are prediction, or scientists made calculations how the observable universe will look like in distant future. And it turns out it will be only us and Andromeda because we are colliding. So Milky Way and Andromeda, and the rest of the sky will be dark. So, so it's getting darker.
Don't turn the lights off now. So I have the lady who asked a question the last time, and then further along, the gentleman in the blue shirt.
So imagine if we were able to teleport Zeno, Achilles, and the tortoise to 2024. Given what you showed with Le Petit Prince and the inverse square law of flux, would Achilles, no, at what point would the tortoise have redshifted out of the view of Achilles? Would we be able to calculate that given our much more advanced calculus today?
You are allowed to ask the audience.
In principle, of course, I'm not as good as to just derive it on a blackboard, but in principle, the metric, the universe can expand as fast as it wants, even higher, faster than the speed of light. So it depends what the universe is doing, right? It's not only about how tortoise moves relatively to their system of coordinates, but also what the universe, space and time are doing. And if in these 2 points where Achilles and tortoise are expanding relatively to each other at superluminal speed, Achilles will never catch up, I'm afraid.
Okay, I have a way simpler question for you, but first of all, thank you very much for painting such a beautiful and rich picture of the universe.
Thank you.
Now, one thing I've been struggling with again and again is how do you picture the thing beyond the observable universe? What is out there, if there is anything, apart from nothingness? But
Well, this is a very
Thank
deep
you.
philosophical question. As naturally, as scientists, we deal with what we can see and leave it to philosophers to think about the universe beyond the observable. There are some methods, like people look for similarities of points at opposite sides of the universe to test if it's closed or if it kind of cyclic and closes on itself or not. But beyond that, we have to deal with data that is limited.
So we have a gentleman
So
here.
just to check my understanding is accurate, the visible part of the horizon has to be within, is limited by the speed of light, because it comes back to us at the speed of light. So that kind of means that for part of the universe, the populated universe, the universe with matter and so forth, for part of that universe to be invisible to us, there must have been an expansion at more than the speed of light to begin with, because, you know, frankly, far out we see very old light. That's true, but it's not, you know, it's light that has been emitted for a long way back. But, you know, the bits that we couldn't see because of this principle of limitation of the speed of light, given that the universe is nearly 15 billion years old, at some point it has to have expanded more quickly than the speed of light. Is this the early part of the Big Bang, so the early part, or is this still going on in some way through some physical principle?
Well, first of all, the inflation, right? The first moments are exponentially fast expansion, right? And then the exact distance out of which we can see, we need to use general relativity and do the integration, basically, and integrate over the variability of space and time exactly to get the exact number. So because the universe accelerates now, we are back to basically square zero with exponential expansion. So that it's not exponential now, but it's accelerated. And at some point, as we were saying earlier, our visible horizon, so it shrinks actually now. So in the past, we could see more than.
But I mean, you know, the very old light, we should still, I mean, originated very long ago, but we should still see it. I mean, that inflation is essential for us not to see. That inflation at higher than the speed of light is essential.
Yes.
For bits of it to be outside of our.
Yes, yes, that's true.
So we have a question in the front row.
Yeah, thank you for the nice talk. So I'm captured by I guess it's similar to the previous question, this sort of horizon that we can't see further on. So I guess when things enter a black hole, we can't see it, right? Just because light can't escape. But in some sense, the information that's of that object is spread or encoded on the surface of black holes. So is there something similar for this outer horizon? Have people explored this sort of?
Not really. There are really parts of the universe that are completely disconnected. I mean, they were at some point within here, right? But then there is exponential expansion. So we don't see these stars at all. They formed after, and they never have been in causal contact with us. It's not like with a black hole that you see them and then they get smeared.
Another question in the front row?
This one's more to do with gravity. If a massive, massive gravitational object were to spontaneously appear somewhere within the universe, would we instantaneously be affected by the space-time distortion of that, or feel its gravity? Would it affect us instantaneously, or would it take time for that distortion to ripple through the universe and reach us?
So that's a great question. Again, recent observations just a few years, or within a few years, show that Einstein's theory is again correct. And even ripples in space-time move with the speed of light. So it wouldn't affect us instantaneously. It would take some time for it to get to us.
You're getting lots of questions because you're giving good, concise answers. Gentleman in the jumper there.
When a photon is redshifted by the expansion of the universe, where does the energy go to?
So that's a great question, which I had to think a lot when I was teaching this. So just a photon itself, in this case, is not a closed system. It interacts with the metric of the universe. So the universe and photon are closed systems. So the photon loses energy, but it goes into the kind of the universal pool.
Exactly. The universe is expanding adiabatically, isn't it?
Sorry?
The universe is expanding adiabatically, isn't it?
That's what we know, yeah, as far as we know of. But the energy of tiny photon won't affect the whole big universe, right? It's just this infinitesimal addition.
Any further questions for Anastasia? There's one right at the back, and there's another one here, depending. So right at the back under the clock.
Can I just add, so just to add to your question, so if we are in a very overdense region, locally it actually collapses, right? So the universe on large scales that expands. So it depends on the local conditions where you are.
Hi there. Yeah, as everybody else has been saying, thanks for an amazing talk, and also the previous talker. You mentioned dark matter and dark energy. I'm just curious, as it's so mysterious, I mean, to your knowledge, how are astronomers and cosmologists going about observing to really get some substantively better understanding of it?
Yes, there
Thanks.
is thank you for the question. There is a lot of effort put into tackling this because it's really the most of the universe, and we want to know what it is. So there are big surveys, like I mentioned, Dark Energy Survey, which measures galaxies, 300 million galaxies they have. And these are tracers of the space and time. Basically, we use them to measure the expansion locally at every point. And maybe it's not adiabatic eventually, but that's something that needs to be tested. That is one thing. So these galaxies will tell us if the expansion is accelerating and how. So we know that it is accelerating, but exactly how it happened in the past. That is one way to measure it. From cosmic microwave background, we also see that there was dark energy and dark matter. There are gravitational lensing experiments. Actually, the first one was done to prove Einstein right in the first place by Eddington. These are, if you look at the distant object, and if there is an intervening mass, the light of this distant object will be lensed. And we see that a lot in current observations. That is another test of dark matter. Then there are many tests that test the particle physics nature of dark matter by thinking about how it would react. So if dark matter is very light, it would create interference profiles in dark matter structures, similar to the ripples on the water if you throw a stone. And this would affect distribution of galaxies and the motion of stars as well. So things like this.
So the last question is this gentleman down here.
Yeah, you just mentioned about star can emit light, so it's should be bright in this paradox. But as we know, there is some light absorbent, like the dark hole. Then, do you have any statistics, or do we have any statistic of how many dark holes there in the sky, or any light absorbent, like there is a lot of abundant gas right out in the space that is also can absorb the light emit in the space and re-emit to all the direction. That is any of this theoretical derivative that we can know if such a light absorption element exists out in the space that can affect this paradox.
Right. If I understood you correctly, it's about how many black holes there are. So black holes, actually, if you're far away enough from black hole, it acts as a normal matter. It won't absorb light, right? Light needs to go very close to it to get trapped, close to the event horizon. So we now know that every galaxy has a supermassive black hole. So it would absorb any light that goes close to it, but not much affecting else, only through gravity. And then stars, some of stars that die end in stellar black holes. So fraction of stars would contribute to small stellar black holes.
So can you please join me in thanking in the time-honored way?